this problem or any problem so far? If anybody has doubts about this problem or any problem prior to this, we talked about crystallization, filtration, drying. We talked about some simple applications for measurement of flow, some very basic things, very simple problems, evaporation, then your separations like reverse osmosis. If anybody has any issues about unit conversions, we talked about these unit conversions, basic concepts. We talked about unit conversion, compositions we talked about. If you have any doubts, just unmute yourself and ask. Otherwise, we'll start with the next problem.
Sir, I have a question, but
Yeah.
it's not a doubt.
Okay, ask. Doesn't matter, doubt,
Sir,
question.
the formula for the mole fraction is N1 N2 upon N1 plus N2.
Bapre, bapre. Wait a second, wait a second. We are talking about compositions. Okay. Now, what are you saying?
The the formula for mole fraction is
Huh?
N2 upon N1 plus N2,
Huh?
and sometimes N1 is very big than N2. So
Huh?
we consider the denominator as N1 only.
Right.
So till what value we can consider that?
No, no. So, suppose I say oxygen and nitrogen. So, if I take mole percent in air, let's say, so air we are saying is 21 mole percent oxygen, 79 mole percent nitrogen. Okay, forget about other things. It's 20.8 and so on. So don't worry about all those issues just now. Just assume that air is 21% mole percent oxygen, 79 mole percent nitrogen. That means what do we mean? That if I take basis as 100 moles, out of these 100 moles, 21 moles, we can say gram moles if you like, or kilomoles if you like. If I take basis as 100 kilomoles, 21 kilomoles will be oxygen and nitrogen would be 79 kilomoles, right? So mole fraction of oxygen would be 21 divided by total, which is 100, right? So 21 divided by 21 plus 79. Now, so this is 0.21. Now, suppose 21 is far less than 79. Obviously, this is not true, right? So if I assume that
Yes, sir.
21 is far less than 79, then mole fraction would be 21 divided by 79. Okay, so 21 divided by 79. How much is this number? This is 0.265, 266. Let's say 0.27. By neglecting this, what I'm trying to say is there are no um, fixed answers. This is not a fixed 12 standard class that something you will get wrong and something you will get right. Okay? If I ignore this 21, how much error we have made? 0.21 versus 0.27. This is an error of 0.06 in 0.21. So percentage error is 0.06 divided by 0.21 into 100. That error is 28.6%. Error is ignoring, oops, error is ignoring 0.06 out of 0.21 into 100. That is 28.6%. Is 28.6% error acceptable? No, it is not. Suppose if it was 2% and 98%. So the mole fraction would be 2 divided by 100, which is 2 divided by 2 divided by 2 plus 98. So this is 0.02. Okay. If we neglect now, we say that 2 is far less as compared to 98, then the mole fraction would have been 2 divided by 98. 2 divided by 98 into 100. We are talking about fraction only. Is 0.0204. Correct. How much error have we made? Error that we have made is 0.0004 in 0.02, isn't it? Into 100. Do you agree with this?
Yes, sir.
So this error is now 2%, 2.04%. Now we have to see whether this 2.04% error is acceptable or not acceptable. Right? Is the error 2.04%? Is it less than the measurement accuracy? Is it less than my allowable error? If you are measuring some if you are measuring some component in ppm level, then obviously 2% error in a ppm level is not acceptable. But if you are making a measurement of something like 20, 30, 40 mole percent, then 2% may be acceptable. So this allowable depends on the situation, right? Do you agree with that? There is no
Yes,
universal
sir.
answer. That's what
Yes,
I'm
sir.
trying to say. There is no formula. There is no cutoff lower limit.
No, sir, in a question I
Some
got
cases, yes, I
mole fraction and
2%
10 power minus 3. So I
hmm,
thought, why would we consider that if n1 is so big than n2?
neglect.
Neglect it.
Yeah. If you want to neglect, if the error you are making is very small, it's okay,
Okay, sir. Thank you.
right? Okay, shall we go forward? Shall we go to material balances now with reactions? So some basic concepts we are going to look at. So imagine we are talking about let's say steam reformation reaction. Let's say steam reforming. So reaction is methane plus gas, steam reforming of natural gas. We'll talk about where this is required. So natural gas is predominantly methane. So if I say this reaction occurs at high temperature, it's actually an equilibrium reaction, but right now let's write it as like this: CO plus hydrogen. Now, is it okay to say that 1 kg of methane reacts with 1 kg water, giving 1 kg CO plus 1 kg hydrogen? Is that what this reaction conveys?
No,
No,
sir.
sir,
No,
kilomoles.
right. So when I'm saying that methane I write with reacting with water, that means we are saying one molecule of methane is reacting with one molecule of molecule of methane is reacting with one molecule of water. Is that what I mean? So if I say that, then either I say in terms of one molecule, or I can say in terms of 1 gram mole methane reacts with 1 gram mole water. Or if you're talking about tons and tons of quantities, you might want to say 1 kilomole of methane reacts with 1 kilomole of water, giving us 1 kilomole of carbon monoxide and 1 kilomole of hydrogen. Is that statement correct?
So 3 kilomoles, right?
Right. So this statement also is not correct. Why is that? Why is this statement not correct?
The stoichiometry is wrong.
Stoichiometric coefficient is not balanced.
Yeah, we have not balanced our reactions in the sense that if I say, well, let me just show you. If I say 1 kilomole of methane and 1 kilomole of water gives me 1 kilomole of carbon monoxide and 1 kilomole of hydrogen. This means 1 kilomole is 16 kilograms. Water 1 kilomole is 18 kilograms. Carbon monoxide 1 kilomole is 28 kilograms. Hydrogen 1 kilomole is 2 kilograms. So 16 plus 18, 34 kilograms would react, and I will get only 30 kilograms. That's not possible because we are violating material balance. No other reaction is happening. Obviously, what I need to do is to balance this reaction. Right? When I say balance this reaction, what I would mean is I have to have same number of carbon atoms on the left hand side, right hand side, same number of hydrogen atoms on left hand side, right hand side, same number of oxygen atoms on left hand side, right hand side. So obviously, if I start balancing out, if I say take 1 mole of if I take 1 mole of methane, obviously I will require, if I take, let's say, 1 mole of methane, I have 1 carbon atom, no other carbon atom in this molecule, no other carbon atom in this molecule, and therefore I will get 1 molecule or 1 mole of carbon monoxide starting with 1 mole of methane. And now I have 1 mole, 1 atom of oxygen on the right hand side. So I need to have 1 atom of oxygen coming from water. And now I have 4 plus 2, 6 atoms of hydrogen on the right hand side. And therefore I would need 3 hydrogen atoms or 3 hydrogen molecules on the right hand side. So now the correct statement is our 1 kilomole of methane reacts with 1 kilomole of water, giving us 1 kilomole of carbon monoxide and 3 kilomoles of hydrogen. Now if you see 16 plus 18, 28 plus 6, now 34 kilograms on the left hand side, 34 kilograms after reaction. So now material balance is satisfied. Why? Because we have satisfied the individual number of atoms of each of the elements that are taking part in the reaction. So when you are talking about reactions, one of the first things that we will have to do is to balance the reactions. Okay. And when we have balanced our reactions, then Kg is reacting or Kg is input will still be equal to kg's output, but kilomoles input will not be equal to kilomoles output, right? In this particular case, 1 mole of methane, 1 mole of water giving us 1 mole of carbon monoxide and 3 moles of hydrogen. So I have 2 moles reacting, but I am getting 4 moles after the reaction. So when the reactions are happening, our moles of raw materials is not going to be equal to moles of products, because stoichiometry reactions have to be balanced to account for the total mass or total atoms of each of these components or each of these elements that are reacting or taking part in the reaction, right? So these 3 concepts we need to remember when we are doing our reactions. And remember all our other concepts that we have looked at so far. What are the concepts that we have looked at so far? First thing that we looked at was looking at drawing a process flow diagram or a process block diagram. Process block diagram. That is the first thing and first step that we should do in all our problems. Second is to write the basis. Basis is your start point for your calculations. Using that basis, we are going to do all these calculations. third concept that we saw was looking at control volume. What is the control volume that we are looking at? Imagine. So one important point that we need to discuss from last time, remember our crystallization, filtration, drying problem. Well, we took our evaporators problem. So where is that crystallization? Yeah, this is that crystallization, filtration, drying problem. What we did was we looked at individual block. We took a control volume here on this evaporator block and we did material balance. Then we looked at this cooling block and we took this as a control volume and we wrote balance over the hot solution coming in and the slurry going out. Then we took this as a control volume, the filtration as a control volume, slurry coming in, wet cake going out, and mother liquor going out. Then we took dryer as a control volume. Then we took dryer as a control volume and we did a balance over this wet cake coming in, water going out because of evaporation, and the dry solids or dry crystals that are, or dry powder, whatever solid form of P and I is going out, right? If you want to know whether your answers are right or wrong, you can even do an overall control volume. So overall control volume, if I take something like this, I can even do material balance on the whole control volume. Overall control volume consisting of all blocks. If this is our overall control volume, what comes in is the aqueous solution goes out. Aqueous solution comes in containing P, I, and water. P was 5%. Right? P was 5%. I was 1%. Water was 94%. Water went out of the evaporator. First evaporator, water was evaporated. Then mother liquor came out of that filtration block. Okay. Then the dryer block, water was evaporated. Okay. And then what we had was dry solids, which consisted of P and I. So if I take this overall block, overall plant as a control volume, then I should be able to check whether my answer is right by finding out how many kgs of aqueous solution come in, how many kgs of water gets evaporated, how many kgs of water gets evaporated in the dryer, how much kgs of mother liquor go out, how many kgs of dry solids go out. So overall material balance also should be satisfied. That is one thing you can check. Second thing you can check is balance for P. Right? Whatever P comes from here, all of that P should end up either in the mother liquor or in the dry solids. Balance for I. Whatever I we put in, all that I should go in the mother liquor, or it should end up in the product, because there is no I and P going out in the along with the evaporated water. Whatever water we have put in, all that water should go out in the evaporated water plus whatever goes out in the dryer. So balance for P, I, and W. So you can take different control volumes and do material balance. So control volume can be one block, or it can be multiple blocks. It can be 2 blocks, 3 blocks, 4 blocks, or the whole plant, right? Okay. One more thing that we saw was looking at tie components. So identify components that don't change, that allow you to write material balance across different control volumes. Okay. So these are some of the concepts that we have seen so far. And now we need to look at balancing reactions, inputs, and in terms of mass will always remain same. Input output mass will remain same, but input output kilomoles will not remain same, because when reactions are happening, you could have molecules or moles increasing or decreasing depending on the stoichiometry of the reaction. Some of these are very simple things you might think. You have already done all this right from 8th standard, 7th standard, but when we start doing problems, sometimes we forget some of these simple concepts. Okay, next important thing is I will explain with an example. So let's assume that we have, so the next important point, there are 3 more important points that we are going to discuss today in class. Okay. Imagine that um, I have a car and we are burning petrol in the engine. Okay, and that's what is generating power for the car, for driving the car around. That's what gets me from my house to ICT. Okay, but so imagine that we are burning petrol. So let's say petrol is all octane, pure octane. Let's assume. Okay, assume. So C8H18. Okay, it is burning with air. So oxygen from the air is utilized for burning. Imagine that it is getting burnt completely to carbon dioxide and water. Can we balance this reaction? So if I start with 1 octane, I have 8 carbon atoms on the left hand side. I must have 8 carbon atoms on the right hand side. Okay. Now I have 18 hydrogen atoms on the left hand side. To get 18 hydrogen atoms on the right hand side, I will require 9 moles of water or 9 molecules of water. Now I have 16 plus 9, 25 atoms of oxygen on the right hand side. I need to have 25 atoms of oxygen on the left hand side, and this will become 25 by 2 or 12.5. Okay, so now can you tell me, if we take 1 kg of octane, if we take 1 kg of octane, how many kgs of air would be required for complete combustion of octane? Okay, and we are assuming that air is going to contain only oxygen and nitrogen, 21 mole percent and 79 mole percent. Okay, can you tell me this now? Can you solve this problem? If we take 1 kg of octane, how many kgs of air would be required for complete combustion of octane? Assume that air contains only oxygen and nitrogen, 21 mole percent oxygen, 79 mole percent nitrogen, just for simplicity. We are neglecting carbon dioxide, argon, all those things we are neglecting in the air. Oxygen is 20.8%. We are saying 21% just for simplicity. Calculate and tell me your answer.
Sir, 15 kgs roughly.
Okay. How many kgs you are saying? 15.
15.
Okay, that is one answer.
Sir, 28.34 kg.
Okay. 28.34 kgs is one more answer. Let's just say 28.3. Let's just round off to 3 significant digits. Two answers I have.
So 3.5 kg.
Okay, 3.5 kgs.
3.5 kgs.
Okay, one more
Sir,
answer.
3.48, 3.5.
3.48, so same as 3.5.
2.5 kg.
2.5. Okay, 2.5
Sir,
kgs.
14.7.
Okay, 14.7. So whoever said 15 as a first answer, was it 14.7 or was it 14.9 something? Or
No, so
15
it
point,
was 15.054.
okay, 15.054. So okay, 15.
So 14.96.
14.96.
Sir,
Can
15.
we say it is 15?
Yes.
Okay,
Sir, 15.
so
Sir,
one more answer for
15.
okay, one more answer for
Sir,
15.
15.
One
Sir,
more answer.
16.7
Okay,
kg.
15.7.
So 16.7.
Oh, 16. Sorry.
Sir, 16.7.
Sir, 16.7.
Okay, 16.7. Three answers.
Sir, 16.7.
Okay, one more answer. 16.7.
Sir, 16.7.
Okay, fifth answer. Okay, should we solve? Do you need more time?
Sir, 2 minutes, sir.
Okay.
Sir, may you please show the composition again?
Your voice is very faint. Can you speak loudly?
May you please show the composition of air elements?
Yes. I'm unable to hear you. Your voice is breaking. Who was that? Dharmik.
Sir, 15 kg.
Atharva, how much? You're saying 16.
15, 15. 1 5.
15. Okay. So one more
Oh,
answer for 15.
so
Yes.
sir, I said 28.3, but I want to change it to 3.5.
Okay. So 28.3 goes away. 3.5. One more answer. Okay.
Sir, 15.
16.7.
16.7. One more answer. Somebody said same. Same
Sir,
means what? Which same?
3.5.
3.5. Okay.
Sir, 15.
Sir, 16.7.
Okay.
Sir, 15.
Sir, 15.
Okay.
Sir, 16.7.
16.7 and 15 seem to be two popular answers.
Sir, 16.7.
Yeah. Okay. 16.7 seems to be problem. Aman, you were saying something?
15.
15. Okay.
Sir, 16.7.
Okay. 16.7. Now CRS said 16.7.
Sir, I said 3.5.
Oh, Snail said 3.5. Okay. CRS said 16.7. So 16.7 is the right answer. CR is always right. Okay. Shall we solve?
Sir, I would like to change my answer to 3.5.
All right, 3.5. Okay, ठीक है. It doesn't matter, Hardik. We will go forward. Let's try to solve. Right. So we have balanced our reaction. Now, what basis shall we take for this particular problem?
1 kg octane.
1 kg of octane. Right? Oops. 1 kg of octane. That's straightforward because we are asked to calculate for 1 kg of octane. So straightforward. So now if I have to write reactions, they are reacting based on moles. So I need to convert this 1 kg octane into moles. So octane, I need molecular weight. So molecular weight of octane, somebody tell me.
Sir, 114.
114. So 1 kg of octane corresponds to 1 divided by 114 kgs divided by molecular weight. So it will become kilomoles of octane. Okay, how much is that? So 1 divided by 114.
Sir, it is better to write in moles only because.
All right, it is better to write in mole, but no, but it is also okay to write in terms of kilomoles. That is fine. So this would become 0.00877. We are still sticking to 3 significant digits. Right? Or if you want to write, zeros, that's even better. 8.77 into 10 raised to minus 3 kilomoles. Now, what is the stoichiometry telling me? For 1 kilomole of octane, I require 12.5 kilomoles of oxygen are required for 1 kilomole octane. Right? But I don't have 1 kilomole of octane. How many kilomoles do I have? I have 8.77 into 10 raised to minus 3 kilomoles of octane. So kilomoles of oxygen required would be now 8.77 into 10 raised to minus 3 multiplied by 12.5. How much would this be? 8.77 into 10 raised to minus 3 multiplied by 12.5. This would be 0.109 kilomoles. 1096 if you want, kilomoles of oxygen. Okay, am I supplying oxygen to the car engine or am I supplying air to the car engine?
Air.
Air, right? So if I say that air is getting supplied, so imagine this is your car. This is your car. Okay, this air is going into the engine. So this air should be sufficient to supply 0.1096 kilomoles of oxygen. So in the air, what is air going to consist of? When I take 21 kilomoles of oxygen, along with that, I will get 79 kilomoles of nitrogen, whether I like or I don't like, isn't it? Nitrogen is not required for burning, but when I supply air, if I have to supply oxygen, automatically nitrogen also is supplied along with this oxygen, but I don't need 21 kilomoles of oxygen. What I need is only 0.1096 kilomoles of oxygen. So the amount of nitrogen that will come along with 0.1096 kilomoles of oxygen would be 0.1096 multiplied by 79 divided by 21. How much is this number? Into 79 divided by 21. This would be 0.412 kilomoles. 4125 if you want to be having 4 decimal places or 4 digits, significant digits, 4125. So what I'm actually supplying is air. What is it getting supplied from this air? 0.1096 kilomoles of oxygen and 0.4125 kilomoles of nitrogen. Why? Because this air is going to contain 21% mole percent oxygen and 79 mole percent nitrogen. So I can't supply only oxygen from air. I can't say only oxygen go inside the engine, nitrogen remain outside the engine, right? 21%, 79 mole percent. So every 21 moles of oxygen I admit into the engine, 79 kilomoles of nitrogen are automatically coming into the engine, right? So now what is the weight? What is the mass corresponding to 0.1096 kilomoles of oxygen? It would be 0.1096 into 32 kgs. 0.4125. What would be the weight? What would be the mass of these many kilomoles? 0.4125 multiplied by 28 kgs. How much is this? 0.1096 into 32. This would be 3.5 kgs, and 0.4125 into 28. This is 0.4125 into 28. This is 11.55. What is the total amount?
15.5.
Right? What am I asking? I'm asking how many kgs of air would be required. Why? Because the air handling system in the car, meaning the fan, the air filter, all those things have to handle not this 3.5 kgs of oxygen. It has to handle 15.05 kgs of air, because this 11.55 nitrogen are coming along free with this 3.5 kgs of oxygen. By 3.5 kgs, you will get 11.55 kgs nitrogen free. You have no choice but to admit that nitrogen, isn't it? Do you agree? So somebody said 3.5, but you are only talking about the oxygen part of that air. Actually, it is 15.05 kgs. Okay. Yes, no? Can we go ahead?
Yes.
Yes, sir.
Yes, sir.
Okay. So what am I saying now? Stoichiometry. What is the stoichiometry now?
Balancing of molecules.
What is the
reaction.
stoichiometry for this reaction? 1 mole of octane is reacting with 12.5 moles of oxygen, giving us 8 moles of carbon dioxide and 9 moles of water, right? That's the stoichiometry. Now, suppose to the engine I supply 0.5 kilomoles of octane and 15 kilomoles of oxygen. Do you understand now? Now to the car, I am supplying 0.5 kilomoles of octane and 15 kilomoles of oxygen. Along with that, nitrogen will come, but I am not worried about that because nitrogen is not reacting in this reaction. Right? Do you agree with this? Suppose Mahesh, just unmute yourself and ask. I can't look at the chat when I'm talking and explaining. Mahesh, you raised the hand.
Sir, we took the percentage by weight, so our answer is get wrong.
Which we took percentage by weight?
Air 21% and 79%.
Oh, you took 21% by weight. No, it is 21% by mole.
Okay, sir.
It is not 21% by weight. It is 21% by mole.
Okay, sir.
That's why you got a different answer, 17 point something, 16 point something.
Yes, sir.
Okay, so now, at least you know where you have gone wrong.
Okay, sir.
Doesn't matter, right? 2179 by mole percent. It is actually 20.8 and 0.2% carbon dioxide and so many other things are there, but we are not worried about that just now. We are just saying 2179. Okay, where was I? Yeah. So suppose I say that I supply to the engine 0.5 kilomoles of octane and 15 kilomoles of oxygen. Can you tell me what would be the limiting reactant?
0.5 kilomoles of octane.
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 Yeah. Limiting reactant is one that is stoichiometrically deficient. 1:12.5 is the stoichiometry. So 0.5 would have required 0.5 multiplied by
6.25.
12, yeah, correct. 0.5 multiplied by 12.5, it would have required 6.25 kilomoles of oxygen. Right? What I have supplied is 15, which is more than what is stoichiometrically required. So our limiting reactant is octane. Our excess reactant is oxygen or air for that matter. But suppose I supply 1 kilomole octane and 9 kilomoles oxygen. Now, what is our limiting reactant?
Oxygen.
Oxygen.
Right, oxygen. What is our excess reactant?
Octane.
Octane.
Sir,
Yeah.
sir, limiting reactant and limiting reagent are same, right?
Limiting reactant and
Limiting reagent.
a reagent is anything that reacts, right? Reagent is any substance that is taking part. It may be doing some, not just this reaction, something else it might be doing. Reagent, reactant, they are just different names.
Okay, sir. Thank you.
Okay, one more concept. Let's look at the first case. Let's look at the first case. Let's look at this case. 6.25 kilomoles oxygen were stoichiometrically required. But we supplied 15. How many excess kilomoles did we supply? 15 minus 6.25,
9.75.
8.75.
8.
Okay. So 8.75 kilomoles of excess oxygen we supplied. What is the percentage excess? It is 8.75 is what we have extra supplied, divided by 6.25 that was stoichiometrically required into 100. Right? 8.75 divided by 6.25 into 100. It is 140% excess. Do you agree? Look at the second case. 9 kilomoles of oxygen. That is a limiting reagent. This 9 kilomoles of oxygen, what is the stoichiometric requirement?
12.5.
What is the stoichiometric requirement of octane corresponding to this 9?
0.72.
0.7.
That would be 9 divided by 12.5, isn't it? So 9 divided by 12.5. 0.72. Do you agree? Yes, no?
Yes, sir. Yes.
Yes, sir.
Okay. How many we have actually supplied? We have supplied 1 mole actually. What is the excess moles that we have supplied?
0.28.
0.28. Why 0.28? 1 we have supplied minus 0.72, that is the stoichiometrically required. So 0.28 kilomoles of excess we have supplied, excess octane we have supplied. What is the percentage excess?
200.
It is 0.28 divided by 0.72 into 100. Excess over what is stoichiometrically required. Okay. So that is 38.9%, 38.89% if you like, or 38.9%. Okay. So the next important point when we are doing reactions, one is to balance reactions. We are going to say kg's input is equal to kg's output, but we are not going to say kilomoles coming in must be equal to kilomoles going out. This is not correct because the stoichiometry is different. Fourth thing that we have to think about is what is the limiting reactant, what is the excess reactant, what is the stoichiometric requirement, and what is the percentage excess. Okay, can we go to the next problem? Anybody has any other doubts? Can we go to the next problem?
Yes, sir.
Yeah. So one of the ways in which we generate energy is to burn something, right? And so in your homes, you are burning LPG or your piped natural gas supplied by Mahanagar Gas if you are in Mumbai or some other places. And that supplies our energy, right? In plants and in power plants, we are burning coal, or we are burning methane, or we are burning fuel oil to generate energy, which we convert to electricity. So one of the ways you might be using electricity in your homes, but the power plant is actually generating energy by way of combusting something. It may be a coal getting burnt, thermal power plant. It may be natural gas based power plant, methane getting burnt. It may be a heavy fuel oil, something getting burned. So there are ways in which we generate energy. One of the convenient ways in which we generate energy is to do combustion. So imagine, we will talk about more about generating electricity and so on as we go along. So imagine that there is a furnace or a combustion chamber, if you like. So these are just some names. Okay. So furnace is nothing but a combustion chamber. There is a flame. We supply methane. Let's say natural gas. Let's assume that it is pure methane, and we are supplying air. Okay. So these gases, the methane will get burnt, energy will be released. We will utilize that energy for whatever purposes, maybe generate electricity or whatever we want to do, we will do from this combustion, and these gases will go out. These are called as flue gases, high temperature. Okay. So what is this flue gas going to contain? We are going to assume that methane is completely burnt to carbon dioxide and water. Oops. Methane is completely burnt to carbon dioxide and water. We are going to make that assumption. So this air, what is it going to contain? It is going to contain nitrogen and oxygen. What is the mole percent? Be careful. Mole percent 79:21. Okay. Here is the problem. Okay. in this plant, let's say in a furnace, methane is burnt with 30% excess air. Okay, so here's the problem. Methane is burnt with 30% excess air. Calculate composition of flue gas in volume percent. This is the problem. Can you do this problem now? You can take 5 minutes. If somebody wants a small break, you can have a break also simultaneously. I will be here only. If you have doubts, you can ask, but solve this problem. I'm just going to get a glass of water. Is everybody clear what is to be found? Has everybody understood the problem?
Yes, sir. Any answers? Sir, do we have to give it in terms of mole?
Volume percent.
Okay, sir.
So the flue gas will contain the water vapor also, no?
Yes,
Okay, sir.
it is at high
Sir, may
temperature.
I?
Yeah.
Sir, N2 is 73%, CO2 is
Wait, 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 wait,
7.4%.
wait. Let me write. Wait a second. So you are saying N2 in terms of volume percent. You are telling me, right?
Yes, sir.
Okay. How much?
73%.
73,
CO2 is 7.4%.
7.4,
O2 is 4.48%.
4.48,
And H2O is 14.95%.
14.95. Okay. You might want to round off so that all of them add up to 100.
Yes, sir.
It is adding up to 99.83.
Wait, sir, I will check.
So if you keep 2 decimal places for all these things, it is carbon dioxide, not carbon monoxide. Okay. Praveen, if you
Yes,
keep
sir.
2 decimal places, it will come to 99.99.
Okay, sir.
So just tell me 2 decimal places for everything.
Okay, sir. 73.05.
Okay, 73.05,
Then it's 7.4. Wait,
7.40,
wait, sir. 7.47.
7.47. Now it will become 100.
So
Yeah.
N2 is 69.38%.
Okay, wait a second. 69.38,
CO2 is 4.05.
4.05,
O2 is 8.45.
8.45,
H2O is 8.11%.
8.11. Do they add up to 100?
Sir, 99.99.
Okay, 69.38. No, something wrong. No, 69.38 plus 4.05 plus 8.
Sir, sorry, O2 is 18.45.
Oh, okay. 18.4.
Sir, same as Praveen, sir.
Atharva, tell me answers.
Same as Praveen, sir.
Same as Praveen.
Yes.
So this one.
Sir, I'm getting N2 is 79.
Okay, now, okay, Ria.
Yes.
79,
Then carbon dioxide is 5.4.
5.4,
Water is 10.8.
10 point, oh, water is 10.8, okay.
And oxygen is 4.8.
4 point?
4.8.
4.8.
It's
4.8.
adding up to 100.
Yeah,
Okay.
great.
Sir, my also same with Praveen.
Nishant. We will wait for some more time.
Sir, I'd like to change my answer, and my answer
Okay.
would match Ria's answer.
Your answer would match Ria's answer. Okay. What mistake did you make, Arya?
Sir, the number of moles of oxygen, I had counted it incorrectly.
Okay, okay. I don't know. There is still some mistake. Either this first set is right or second set is right. I don't know which is right. We will wait for some more answers.
Sir, can you show the formula for excess percent once again in the previous slide?
Excess. Okay, okay. Same. Excess, percentage excess. What have we said? Percent excess is how many excess moles that we supplied of the reactant, whatever was excess, divided by what was stoichiometrically required. Into 100.
So
Amount.
stoichiometrically required is what is used basically.
No, stoichiometrically is required is based on what is the reaction.
Okay, yes.
How
Sir.
many moles of stoichiometrically required is what is based on reaction. In this particular case, 1 mole of octane is requiring 12.5. So stoichiometric requirement is 12.5. I can supply 500 also. I can supply 1 also. But what is stoichiometrically required is 12.5.
Yes, sir.
So my answers are matching with the first set.
Praveen seems to be popular person. Praveen, can you take a photograph and send your answers by photograph to maybe Ria? Ria, you can take a photograph and send it to Praveen. Let's see who is correct, who's wrong. You
Sir,
have to
I
be,
do very rough calculations.
no, whatever it is.
Okay, sir. Sending. Sir, do I have to share it on screen or send it them personally?
You can send it personally because Ria, you better check Praveen's answers and you better send your answers to Praveen. And Praveen, you better check Ria's answers. One of you is right, or maybe both are wrong. Both cannot be right. Other people, any answers other than
Sir,
this?
I will go with first answer.
Sir, first one.
First answer.
Oh,
Yes, sir, the first answer.
Sarva. Who hasn't answered so far? Rishabh. Keshav Rajput, are you there? Your answer?
So the first set of values.
First set of answers. Okay. Other people, do you need more time or shall we see on the screen? Somebody say something. Do you need more time or should we solve the problem?
Sir, solve the problem.
No answer means we should wait. Maybe just 1 or 2 minutes. Anybody else? Any other answer? Should we solve now or wait for some more time?
So the first set of values.
Okay. Do you need more time or should we solve?
Sir, solve.
Okay.
Solved, sir.
Okay. What am I told? We are told that we have 30% excess air. Right? And we want this flue gas composition in terms of mole percent. And mole percent and volume percent, they are the same. We talked about that last time. Okay. So basis, what basis can I take? What is a convenient basis
100.
here?
100 mole.
Right, we can take 100 gram moles of what?
CH4.
Methane, right? We can take 100 gram moles of methane as a basis. So 100 gram moles. Okay. Now what is the reaction? Methane plus oxygen giving us carbon dioxide and water. So if I take 1 mole of methane, I will get 1 mole of carbon dioxide, 4 hydrogens. So I will have 2 water generating, and I will require 1 and 2 moles of oxygen. Right? Do you agree with that? So if I take 100 gram moles, what is the stoichiometric requirement? What is the stoichiometric requirement of oxygen? It is 200 gram moles. What is our percent excess? 30% excess. So how many excess moles of oxygen have we taken? It is 30% of stoichiometrically required, which is 200, which is 30% of 200 is 60 gram moles. So what we have actually supplied is 260 gram moles of oxygen. So what we have actually...
Hello, sir.
Yes, yes.
Sir, but the excess is 30% of the total air supplied. No?
Okay. All right. All right. So what is the stoichiometric requirement of oxygen? 200 gram moles. Dharmik, up to, is it okay up to here?
Yes, sir.
Okay. So now 21 gram moles of oxygen if I supply, I get 79 gram moles of nitrogen automatically along with the 21 moles because I am supplying air. So if I wanted to supply stoichiometrically 200 gram moles of oxygen, how many nitrogen would come in? It would be 200 into 79 by 21. Do you agree with that?
Yes, sir.
200 into 79 divided by 21. It is 752.38 gram moles of nitrogen. What is the total gram moles of air? Stoichiometrically required? It is 200 plus 752.38. Do you agree with that?
Yes, sir.
This is 952.38. How much excess air are we supplying?
30%.
30% excess. So that means extra supplied is 30% of this 952.38. This is 285.71 gram moles. What is the total air that we have supplied? It is what is stoichiometrically required, 952.38 plus 285.71. 952.38. This is 1238.09. 094 if you want. Right? This is still going to contain 21%, 79%.
Yes, sir.
Okay. So what is 21% of 1238.39? 1238.094? Dharmik.
Yes, sir. 0.21 into 1238.
How much is that?
259.98.
260.
Yes.
All right. Do you realize that whether I do it this way or I say that 200 gram moles is required, therefore we will supply 200 plus 30% actual supplied is equal to 260 gram moles O2, and 260 gram moles of O2 correspond to 260 into 79 by 21, which is 260 into 79 by 21 is 978.095 gram moles nitrogen. So total air plus 260 plus 978.095, that is 1238.095. Do you realize that either we do this or we do this, they are the same?
Yes, sir.
Thank you. Can we go ahead now?
Yes, sir.
Okay, so how many gram moles of air have we supplied? Oxygen, we supplied 260. Nitrogen, how much did we supply? 978.095. I'll just round off, right? 978.095 I'll just round off. Who will bother doing all this? 978.1. All right. Now, can we go forward? Yes, no.
Yes, sir.
In the flue gas, am I going to have any methane?
No,
No, sir.
Why not?
because
We
it
have
has been
assumed that all
complete
the methane
reaction.
is used.
We have assumed that all the methane has reacted. Why? Because methane is our limiting reactant. Air we have supplied in excess. So methane, whether I write or whether I don't write, it is the same. Is there going to be nitrogen?
Yes, sir.
Yes, sir.
Now, if I take this as a control volume, nitrogen comes in. How much does it come in? 978.1 gram moles come in. Is there any nitrogen that is reacting? No. So all the nitrogen will go away. Tie component, if you like. Oxygen. 260 I have supplied. Out of the 260 we have supplied, how much has reacted?
200.
200. So what is the material balance over the control volume for oxygen? Whatever comes in minus whatever has reacted is equal to what has gone out. So 260 is supplied minus 200 that is reacted. How much will go out? 60 gram moles will go out. Okay. When methane reacts, carbon dioxide will be formed, water will be formed. So if 100 gram moles of methane react, how many moles of carbon dioxide are generated? 100 gram moles. So now what balance can I write for carbon dioxide? Whatever comes in plus whatever is generated by way of reaction must be what is going out of the control volume. What comes in? 0. What is generated? 200. Stoichiometry. What goes out? 200. Okay. Water. Every 1 mole of methane that reacts, 200 moles of water would be generated. 200 gram moles of water would be generated. Again, balance for water. Whatever comes in, 0. Whatever is generated, 200 gram moles. So what goes out is, what goes, you should stop me now. 1 mole of methane that reacts, 1 mole of carbon dioxide is generated. So 100 gram moles of methane react, 100 gram moles of carbon dioxide is generated. And 1 mole of methane reacts, 200 gram moles of water will be generated. So what goes out will be 200 gram moles. Do you agree with that? Anybody agrees? Anybody disagrees?
Yes, sir, I agree.
Total. What is the total?
Sir, explain again.
Yes, Prakash.
I was saying, please explain again.
Explain which part again?
Sir,
what is the balance for carbon dioxide? Whatever comes in plus what is generated must be what is going out. What comes in? No carbon dioxide comes in. How much is generated? Every 1 mole of methane that reacts, 1 mole of carbon dioxide is generated. So if 100 gram moles of methane react, 100 gram moles would be generated. So what goes out would be 100. Same way for water. What comes in? Nothing. No water comes in to this control volume. How much is generated? Every 1 mole of methane that reacts, 2 moles of water are generated. So 100 gram moles of methane that react, 200 gram moles would be generated. What goes out must be 200. Prakash, is that okay? Prakash. Are you there? Is your doubt cleared or not cleared? What was your doubt? Ah. Prakash, don't write in the chat box. I don't have time to read the chat box. So what is the total? 1338. Okay. What is the volume percent of nitrogen? 978.1 divided by 1338 into 100. That is 73.1. Right? Oxygen 60 divided by 1338 into 100. 4.48. Carbon dioxide 100 divided by 1338 is actually 1338.1 if you want. Okay. Just add them up. So 100 divided by 1338.1 if you want. This is, if I write everything to 2 decimal places, 7.47, and this is 60 divided by 1338.1 into 100, 4.48. That's okay. 978.1 divided by 1338.1 into 100, 73.096 if you want, 73.1, that's okay. Water 200 divided by 1338.1 into 100. .95. So this is correct, this is okay, this is okay, this is okay, right? Ria, Arya, have you realized where you had gone wrong?
Yes, sir.
Okay.
Yes, sir.
Okay, fine. Now one more small point that we need to discuss is that whenever gases are there, one of the ways in which we measure gases is by displacement. So we absorb oxygen and find out what is the total volume. We absorb carbon dioxide and find out total volume. But when we absorb something, water automatically gets added or subtracted because it is going through water. Have you ever done experiment and collected a gas? So you have
Sir,
some.
I've tried, but it was very difficult.
You have done any experiment where you generated some gas by heating something?
Yes, sir.
And then you have
by heating ammonium dichromate, I tried to collect ammonia gas.
Right, and what you do is you collect this in an inverted tube if you want,
It was not that simple.
I know it's not that simple. The point that I'm trying to say, or point that I'm trying to make, is this gas gets bubbled through this water. So we don't analyze the water percentage, we analyze all the other components of the gas that are collected in these test tubes, isn't it? So what we have is nitrogen, oxygen, carbon dioxide and water. If you write gram moles, let's just write that quickly. 978.1, 60, 100, 200, total 1338.1, right? And the volume percent or mole percent that we have calculated based on all of this is based on the total composition, total amount or total gases that are all present in the system, right? But we don't really like to report water because whenever we collect and we measure, it is automatically bubbling through the water. So some of this water may condense, or some of this water may get added, extra water may get added to the gas, isn't it? So reporting water is not always a good idea. What we try to do is actually report the gases on dry basis. dry basis means without water. So on dry basis, I have only three components: nitrogen, oxygen, and carbon dioxide. What are their gram moles? 978.1, 60, and 100. On the dry basis, total is 1138.1, and composition on dry basis is 978.1 divided by 1138.1 into 100. This is 85.94 volume percent. Oxygen, it is 60 divided by 1138.1 into 100. This is 5.27. Carbon dioxide is 100 divided by 1138.1 into 100. This is 8.79. Okay. So compositions on dry basis are 85.94, 5.27, and 8.79. Actual composition on wet basis is 73.1, 4.48, 7.47, and 14.95. Do you see the difference? This is actual wet basis, and this is dry basis. Is that okay? So the next point that we are talking about, next concept that we have talked about, is wet basis and dry basis. Especially when we start talking about things like analysis of gases. Okay, can we go to the next problem? Any other point? Can we go to the next problem?
Yes, sir.
Yes, sir.
Yes, sir.
So here is a next problem, very similar to the problem that we did. Okay. Very similar to the one that we did just now. So again, imagine there is a furnace. Horrible. So imagine there is a furnace. Still doesn't look right. Anyway, it will do for now. Okay. So we are burning some hydrocarbon. It can be a pure hydrocarbon. It can be a mixture of 2 or 3 hydrocarbons. We supply air for combustion. So let's assume that this hydrocarbon contains only carbon and hydrogen. I don't know which hydrocarbon we are burning, but it is containing only carbon and hydrogen, and we burn with air. Whatever flue gas we get, okay, I'm going to give you composition of that flue gas. So this flue gas contains nitrogen, oxygen and carbon dioxide. Volume percent on dry basis. Dry basis. On dry basis, it is going to contain nitrogen 85%, oxygen 5%, and carbon dioxide 10%. Okay. What I want you to find is what is the percent excess air that we have supplied, and 2, what is the hydrocarbon right? Is the problem statement clear? These two things I want you to find out. What is the percent excess air that we have supplied, and what is the most likely hydrocarbon that we are burning? This is the composition on dry basis. Solve the problem now. Problem statement is clear, not clear?
So will the hydrocarbon be an alkane only?
No idea. It is going to contain only carbon and hydrogen, that much we know. It may be alkane, it might be alkene, it might be alkyne, it might be cycloalkane, it might be aromatics.
Sir,
Yeah.
the composition of air is same 79:100.
Yeah. Let's assume air is 79 mole percent nitrogen and 21 mole percent volume percent. Hopefully, while we are solving the problem, global warming has not happened to a large extent. Anybody wants any hints? Any answers? No answers so far? Do you think this problem is more difficult?
No, sir. Sir, 2 minutes, sir.
Yeah. Yeah.
Sir, the percentage excess of air is 28.4%, and the hydrocarbon used is most likely ethane.
Okay. Shaurya Raj.
So I got percentage excess as 28.4%.
This is Sarthak. Okay.
So the
Sir,
hydrocarbon
actually,
part
even
is
I got 28.4.
Oh, I thought you said 28.8. Sorry. My mistake.
So same 28.4 air excess. And
So Atharva, what is the hydrocarbon likely to be?
ethane only, sir.
Ethane. And who else was saying? Shaurya was saying. Who else was saying? Who was the third person who gave the answer?
so Sarthak here. So I'm doing the hydrocarbon part.
Okay. Sarthak, yeah. Sarthak. Your faces are not in front, so I can't make out.
Yes, sir. Even I got 28.4.
Punch. And hydrocarbon?
I'm working on that.
So, Sarthak, tell me, how many unknowns did you have? 1, 2, 3, 4?
So I took the hydrocarbon as X and Y, CXHOI. So two
two
unknowns.
unknowns. Okay. Shaurya Raj, how many unknowns?
Sir, two unknowns, but I assumed one of them and I just found the ratio
So
and
another one. Okay. So assume one of them. Assume X is equal to 1 and solve everything based on that.
Yes, sir,
But
that
yeah,
that
okay.
way.
So still okay. One unknown maybe. Can you do this problem without any unknowns? Shaurya Raj, Sarthak, can you try doing this problem without assuming X and Y?
Yes, sir. Same answers for both frequency and hydrocarbon. So without considering X and Y, we can use the number of moles of CO2 and the excess of oxygen that is given. So we know the total amount of oxygen stoichiometrically used, and then we can deduce the amount of hydrogen also hydrogen used as water that would be present in the hydrocarbon.
Okay, how many people have understood what Arya has said? You're right, Arya. Let's just wait for a few minutes for other people to solve. So
Sir,
Arya,
I
you
got
used
the
how many
same,
unknowns?
So I didn't have any unknowns as such. Like
Okay.
everything was given.
Okay, okay. All right. Aniruddha, you were saying something?
I got the same answer, so 28.4% excess of air and ethane.
Okay.
Yes, sir. Same answer.
Oops. Not here.
Sir, same answer both.
If everybody's getting same answer, there's no fun. Other people, should we wait? Should we solve?
Wait.
Okay. How much time, Rishabh? 2 minutes, 3 minutes, 5 minutes? Okay. How do you think this graph looks like? Number of people attending versus time.
Rectangular hyperbola, I guess.
Good guess. It is definitely not a straight line. It is definitely not a linear. Maybe it is exponential. Usually it's a first order process. Or maybe second order.
Sir, it becomes constant. It does not decrease after a number. That's why I said rectangular hyperbola.
Oh, maybe. So I have another hypothesis, right? So it looks like this. Test is announced here. Test is announced here. Test has been conducted here. Test has been conducted here. Test is announced. Test is conducted. Do you think this model works? If a test is announced, yeah, then suddenly people wake up, suddenly people attend. I mean, test is done. Next class, definitely there's no test. Plateaus. Next test. Oh, we are recording. I should not be recording all these things.
Sir, I'm having a different answer.
Praveen, excellent. What is the answer?
Sir, its excess is coming 21%.
Okay. And hydrocarbon
And
is likely to be
gas is coming as propane.
propane. So C3H8. Maybe you are only right. Others are all wrong.
Yes, sir, I was taking so much time. That's why everybody was giving
It's okay.
a different answer.
Maybe you're right. Maybe everybody's wrong. Rishabh, can we start? Can we solve?
Yes, sir.
You wanted
Sir, 2 minutes more, sir.
Okay, Hardik.
Sir,
Okay. 2 minutes.
excuse me, sir.
Yeah.
So I'm getting the hydrocarbon as propene.
Propane, right? C3H8. Or propene, you are saying.
Propene.
So C3H6. And excess air?
Sir, 1 minute, sir.
Okay, let's start solving. Now we know everything about this flue gas, or at least we know the composition on dry basis in terms of volume percent. Can we take a basis as 100 gram moles of the flue gas? That's one way of doing this problem. So our basis is 100 gram moles of flue gas. if it is 100 gram moles of flue gas as our basis, we will have nitrogen 85 gram moles, oxygen 5 gram moles, and carbon dioxide 10 gram moles. Now, if we are going to take this as our control volume, nitrogen is going to remain unreacted. So that's the tie component. So can I say that nitrogen would be 85 gram moles coming in? There is no other place that nitrogen can come in. If nitrogen is 85 gram moles, oxygen would be 21 divided by 79 into 85 gram moles. 21 divided by 79 into 85 gram moles. This would be 22.59 gram moles. Do you agree with that?
Sir,
Yes,
but oxygen is 5 gram moles in the question.
So are you saying that if oxygen is 5 gram moles here, 5 should be coming from here? Is that what you're saying? Om, is that what you're saying? Is oxygen remaining unreacted or is oxygen reacting?
Sir, oxygen is reacting.
Right. So whatever comes in minus whatever has reacted must be what is going out as 5.
Yes,
Isn't it?
Yes, sir.
Okay, but for nitrogen, is nitrogen reacting?
No, sir.
No. So whatever nitrogen is going out, 85 gram moles is going out, all of that, no nitrogen is coming from the hydrocarbon. All the nitrogen must be coming from air. So it must be 85 gram moles of nitrogen in the air that we have supplied. And if we are supplying 85 gram moles of nitrogen, automatically along with those 85 gram moles, would we not have 21 by 79 into 85, which is 22.59 gram moles of oxygen being supplied? Don't you think so, Om?
Yes, sir. Yes.
Okay. Now let's look at this very important point. Along with this flue gas, I also have water, isn't it? Now, can we do a balance of oxygen atoms, if you like, or gram atoms, if you like, just like gram moles? Can we have gram mole atoms, if you like? .59 oxygen molecules are coming, which means 22.59 multiplied by 2 gram moles of atom oxygens are coming in. Om, is that okay? So if you like, 45.18 gram mole atoms of oxygen. O, if you want. I should not say O2, I should say oxygen. This 5 corresponds to 10 gram mole atoms, if you want. This 10 corresponds to 20. Om, are you with me?
Yes, sir.
So together it is 30 gram mole atoms of oxygen that are present as oxygen gas or carbon dioxide gas. So how much water would be present? 45.18 that has been supplied minus 30 that is appearing. So then this must be 15.18. This must be 15.18. Do you agree with this?
Sir, can you repeat?
Sarthak, which point onwards should I repeat? If I look
at
the
H2O part.
Okay, if I look at the oxygen balance, 22.59 multiplied by 2 So that is 45.18 gram mole atoms of oxygen if you want, right, is what we have supplied. I have 5 gram moles of oxygen gas, O2, which corresponds to 10 of oxygen atoms. I have 10 gram moles of carbon dioxide gas, which corresponds to 20 gram atoms or gram mole atoms if you want. So together 10 and 20 is going to correspond to 30 gram mole atoms of oxygen as O. So 45.18 gram mole atoms of O are supplied. 30 gram moles are accounted for here. So 45.18 minus 30, which would be 15.18, would be gram mole atoms of O appearing in H2O, which means 15.18 gram moles of water must be getting formed.
Yes, sir. Got it, sir.
Got it?
Thank you, sir.
Right. Molecules are reacting. Oxygen molecules are reacting with the hydrocarbon, but overall there has to be a balance of all the atoms that are coming in. Atoms are not destroyed. Carbon atoms are not destroyed. It may be in hello, are you able to hear? Sorry, the connection had gone.
Yes, sir.
Right. So, okay so far?
Yes, sir.
You got everything on the left hand side so far. We have got nitrogen, we have got oxygen, we have got
You're not presenting the screen.
yeah. Now only thing that is remaining is our only thing that is remaining of carbon are appearing in this carbon dioxide. So that means I must have 10 gram mole atoms of carbon dioxide of carbon coming in. Hydrogen is present as H2O.
Sir, the screen
Yes.
is not being shared.
Oh, I'm so sorry. This connection has created a problem. Right. Right. So now we have got. Now is it visible?
Yes, sir.
Yeah. Thanks. Sorry. So now we have got nitrogen here, oxygen here. We know the gram moles. We know the gram moles of nitrogen. nitrogen, oxygen, carbon dioxide, water in the flue gas. Now only thing that is remaining is our carbon and hydrogen. Right now, again, if I do atom balances, I have 10 gram moles of carbon dioxide appearing in the flue gas, which corresponds to 10 gram mole atoms of carbon, if you like. So this gram mole atoms, if you want, must be 10 for the carbon. Right? We have 15.18 gram moles of water that is formed. Right? So the amount of all the hydrogen that is there in the water has to be coming from this hydrogen in the fuel. So this hydrogen gram mole atoms would be 2 times 15.18. So this would be 30.36. Okay, and now you can also calculate the excess air. So now we know that our hydrocarbon is like C10 H30.36 plus oxygen if I write a balance. Now we can find out how much stoichiometrically is required. Excess, we have actually supplied 22.59. So we can calculate now based on the how much oxygen is required and how much we have supplied, we can calculate percentage excess. That is straightforward. You can do this. Okay, shall we stop here for the day? Homework. Solve problems from Himmel Blau's book. Plus some more problems I have shared with you. You can try those as well now. I will share some more.
So will the stoichiometry book by, I don't remember the author, will that also do?
Stoichiometry is?
The book Stoichiometry, I don't remember the author, but if we solve sums from there, will that also
So stoichiometry is Butt and Vora's book.
Yes, sir, Butt and Vora.
That's also okay. Those are simple problems. Himmel Blau's problems are a little bit more challenging, a little bit more complicated. So you might want to start with that. That's also okay. Quiz. So quiz we will have at 2 p.m. 2 p.m. to 3 p.m. Okay. It will be a Google form based quiz. So you'll get some questions. You will have to write the answer on that form itself. All right. You don't have anything at 2 o'clock, right? Arya?
Yes, sir. Please repeat.
You don't have anything at 2 o'clock, right? So we will have
No,
a quiz
sir.
from 2 to 3.
Okay, sir.
Okay, so we will not have Google Meet. The quiz questions will come to you at 2 o'clock on your Gmail address. Google form will automatically come in your mailbox at 2 o'clock.
Sir, will it be like a cat?
It is like a cat only. Na? Quiz is a class quiz. Quiz, all those things correspond to cat only. Na?
Okay.
Continuous assessment is in the various forms. One of them is a quiz. All right. So it will be counted towards cat. Yes, it will be counted towards cat. Be honest. You yourself are the supervisor. Right? So don't discuss with anybody. Solve on, right? So it will come to you at 2 o'clock. Shall we stop, Yash?
Excuse me, sir.
How many questions in the test?
579. Then you will ask me what are the questions also. It is 1 hour, no? So 1 hour, how many questions can be done? Those many questions will be asked. Shall we stop for the day? Yeah.
Sir, when we got the answer as C10H30.36, is it possible? Is it possible that it can be twice of C5H 15 point something?
Yeah, sure. So what it is possible is, so it is likely to be a mixture of something. So maybe it is just, it is like CH3, right? So, or CH, almost like CH3. So C3 and H9 or something like that. Right? C3,
Yeah,
H9,
because
there is nothing.
how can the hydrogen come in decimal then? We will have to convert it to a compound.
Correct. So obviously it is a mixture of hydrocarbons.
So
propane is not the answer, right? It's obviously a mixture of hydrocarbons. Beyond that, we cannot say. We cannot say beyond the ratio of carbon to hydrogen. Isn't it? So it might be a mixture. Multiple mixtures can give you the same ratio. Yeah, somebody was asking something.
Yes, sir.
Is that okay, Ansh?
Yes, sir. It's okay. Yes.
Okay, so quiz will come to you at 2 o'clock. Shall we stop for the day?
Yes, sir.
Yes, sir.
Okay, bye. Have fun.
Thank you, sir.
Bye.
Thank you, sir.
Bye.
Thank you.
I will stop.
Thank you, sir.
Okay, bye. I will.
Thank you, sir.
I will stop recording.
Thank you, sir.
Yeah, bye.